That's great. Thanks, Khalid. Yeah, so our first topic of the day in terms of introducing maybe broadly the data science software stack on Aurora is actually starting with less of a machine learning software stack, but maybe more traditional Python for GPU software stack. And to go over the material, I'm actually going to follow a README that is on our ALCF hands-on HPC workshop GitHub page, and then you can go inside of the data science directory and then further into Intel Python, and that's where you'll see both this README that I'll be using to cover the material, and then you also see 7 examples here. And while we won't be doing a live demo with these examples because Aurora is unavailable, unfortunately, we'll still cover the code, and then within each of these scripts, there's a section at the bottom that outlines in comments the expected output for that code snippet, and so you will be able to validate that you can run correctly all these examples later yourself. So the first topic is Intel's data parallel extension for Python, or DPEP for short. And this is really Intel's Python stack for allowing users to do Python on Intel GPUs without really necessarily having to do machine learning. There's 3 main packages that allow us to do data parallel programming on both CPUs and GPUs. And as Khalid mentioned, these are data parallel extension for NumPy, DPNP. This is really a drop-in replacement or implementation of NumPy for Intel GPU. So in a way, it's fairly similar to CuPy for CUDA devices. Then we have DP control, data parallel control, and this provides utilities for device selection, introspection. You can create queues, allocate data. So it's effectively um, an extra layer of utility and fine-grained control about how to program Intel GPUs. And then Numba DPEX, or data parallel extension for Numba, is really an extension for the Numba compiler so that you can do Numba programming in the same way that you would do on CUDA devices with Numba CUDA, but on Intel GPUs. So first, talking about how do you actually access these packages, it's pretty easy. These are part of the frameworks module on Aurora, all 3 of them. So the users just need to do module load frameworks. And this was done intentionally so that you can enjoy interoperability between these Intel Python packages with all of the machine learning packages as well. So to see specifically what versions this module has, you can execute this command conda list grabbing for the particular packages, and the output is shown here. So these are the versions that you can expect to see on Aurora. In terms of how these packages, all 3 of them are set up, they follow the compute follows data programming model. So that's also similar um, to how PyTorch, for example, performs its offloading. And what this means is that the offload target for a Python library call, or if you handwrite your own kernel using Numba DPEX, you don't have to specify directly when making the call. You don't have to tell any of these packages where that call needs to run. Actually, the target device is inferred from the input data. So as long as you offload the input data to the device that you're trying to target, then the computations will follow that data. And similarly, then the output of any of these functions that you call will be allocated on that same device. So effectively, you need to offload the data, if you think about it, once, and then all subsequent calls will run on that same device and then produce data on that same device. And so to look at a very similar example, we can open the first one here. In this case, we use the DP control tensor API, which I'll cover later on. But here we can just do these 3 lines of code. We can see that we initialize an array just with dpt range on the device, in this case, the GPU device. And then we just call dpt square on that, which just computes an element y square of that array. And this computation is performed on the same GPU device. So you see that we don't have to specify the target. And then subsequently, also the output, this SQX underscore GPU array, is also then created on that same GPU device. And so when you print that, will see that the output array is allocated on the level 0 GPU 0 device. So that's the default device. Now going into these three packages, the first one is DPNP. Again, this is really an extension of NumPy using DPC++ so that you can perform NumPy on Intel GPUs. So very similar to CuPy. And so if you're coming from an NVIDIA system and you were using CuPy, then this would really be your first line of porting by effectively doing a drop-in replacement of what you were doing in CuPy or in NumPy with DPNP. One thing to note, though, is that there isn't a full coverage in DPNP of NumPy and CuPy. However, it's very close. And so I've added here a link to the comparison table so that you can make sure when you're doing this porting that the CuPy or NumPy functionalities that you're trying to offload are actually implemented in DPNP. As I mentioned, there's very close to parity compared to CuPy. So I think most of the functionality should be there, but if you're running into any issues, let us know through our support, and we can work with Intel to accelerate development of that particular function. Um, in DPNP, all array creation routines and random number generators have additional keyword. I'll cover those in a second, but those allow you to have, again, some sort of control over where these arrays are allocated, what type of memory you want to use. Now, again, for another short example to see how DPNP works, we can take a look at this second one that I have here in the repository. You can see that, again, very similar. If you're familiar with NumPy or CuPy, this shouldn't be new code to you. We import DPNP as NP, and then we can create arrays. One thing convenient to note is that actually the default device is the first GPU device on the Aurora nodes. And so actually, if you want to target the GPUs, you don't actually have to specify the device at all. You can just use the default device. So you can see if we create just a simple array and then we print the device, you'll see at the bottom here from the expected output that that is, again, GPU 0. And then I'll cover this again in a little bit, but there's a sickle queue associated with each of these arrays. And so if you're interested in that queue, you can actually access it. It's sort of carried with the array object. And then sort of similar to what we saw earlier with DP control, if you execute NP functions, again, those are run on the same device as the initial array, and same, the output array is on that same device. And so you can see here that the result Y is located on that same device. So again, this should look very similar to just NumPy or CuPy code, which was exactly the intention of DPNP. So fairly straightforward. The next package is DP control. This is sort of an extra layer of utilities because it lets users access devices supported by the SQL runtime. What this means is that you have device introspection APIs. You can have more fine-grained control on creating SQL queues, memory allocation, submit even some custom kernels. So we have some examples here in this repository as well as in our documentation. But if you're there's a lot that DP control can offer, and so I do have a link to the official documentation since we can't really cover all of its functionality. But the first thing that we can take a look at is an example doing some device introspection. So here we would import DP control at the top. And then, for example, we can list the SQL platform, which has information on the devices in the node. So here we can do DP control LS platform with particular verbosity level. And so you can hear at the bottom that it shows the runtime being run, its version, the vendor, what the backend is, and the number of available devices. So it gives you sort of a high-level overview of the system you're running on. And then you can get some fine-grained control. So for example, you can call get num devices. Again, you can specify the type, although the default is the GPU. And so this allows you to get the number of devices. You can also get the devices back as a list. Again, this then allows you, for example, to here we can list over those devices and print the properties of each of them. So if you go down, you can see that I found 12 GPU devices. That's because the default is to see each tile of the Intel PVC on a node as a separate device. So there's 6 PVCs, 2 tiles each, which gives us 12 GPU devices. And I'll talk a bit more about that. And then here we just again list some properties of those devices. One thing to note is you can do sort of the same thing, but with the CPU. So at the bottom here, we can use DP control APIs to query whether this node has any CPU devices. And you'll see from the expected output that actually this returns false. And I'll talk about that a bit later, why that is. So this is, again, a short example of some of the things you can use DP control for in terms of querying and trying to understand what you're running on, and then have fine-grained control about which devices you can work on. So then going back to the main README, another thing that you may have seen, in the first example, is that DP control also gives you DP control tensor, which is a tensor library, again, implemented using DCP++. So this is fairly similar to actually what DPNP gives you. So there's a bit of overlap here. And it does similar things. You can do array creation, manipulation, and some linear algebra. So again, very similar to DPNP. And we refer you to documentation to look at that. What we see is that most of the work can be done with DPNP in terms of array creation and manipulation, and DP control really gives you access to device introspection and then fine-grained control. So this is where I wanted to then actually dive into some of that fine-grained control. And these notes apply to both DPNP and DP control. So for example, all the array creation APIs, we saw some of them in these examples. You can pass as arguments the device, the memory type, as well as the SQL queue. So for example, the default device, as already mentioned, is GPU 0 with device memory type. So if you just do this simple call here without specifying anything else other than, for example, the array itself, what you will create is an array on the device memory of GPU 0. But you can also then allocate similarly on GPU 1. All you would have to do here is specify what device number you want, as shown here. You can also then allocate on the unified shared memory, and you can then specify that with this USM underscore type argument of the array creation APIs. The other thing I mentioned a couple of times is you can use DPNP and DP control to create SQL queues, and then you can allocate objects or arrays specifically on those queues. So a very short example is here, where you can see that we import both DPNP and DP control. We use DP control to get a list of the devices. Again, these are the default GPU devices. And then we can use, again, DP control to create a SQL queue on, in this case, the second device in that list. That returns this queue object, which then we can pass to a DPNP array creation API to say that we want this array specifically to be associated on that queue and that device. We can take a look at a slightly more complicated example. Here, it combines things we've seen before. So maybe skip the first few calls here, but I'll focus on this one, which it's looping over the devices, and it's actually then instantiating a queue, a SQL queue on each of those devices and storing those in a list. What that means is that we can loop over those devices again, and then we can call, in this case, just a simple function that allocates an array. And then each array allocation instance in this loop gets the different queue that we allocated in that loop above. And so then when we print the device of each of those arrays that we've allocated, you can see here at the bottom in the expected output is that you see that we've allocated an array on each of the GPU devices available on a node. So again, this is building on what we saw earlier, but just some information how you would get the fine-grained control you may want in terms of making sure that you can create the queues on specific devices and then allocate arrays, and therefore then subsequent computation are then going to be associated with that same queue as well. The other thing to note, though, is that you need to, when you call some functions, whether that's in DP control tensor or DPNP, if an input to a function takes two different arrays, you have to make sure that those are on the same device or associated with the same queue. Otherwise, you will get an exception. But you can copy arrays between devices with this DP control tensor as array, and that will effectively do a copy so you can access, in a way, arrays allocated on separate memory. The other thing to note is that there's a bit of understanding about how we can manage CPU and GPU devices on Aurora. This is true not just for the Intel Python stack, but also for the AI frameworks. So by default on Aurora, this one API device selector environment variable is set to level 0 GPU. What this means is that the GPU are the default devices, which is nice. It means that you don't have to, as we saw earlier, specify a particular device to target the GPUs, but it also means that those are the only devices visible to DP control and other applications that are using SYCL. You can also confirm that by running SYCL ls, for example, on a compute node. This is why DP control has DPU devices, as we saw earlier, returned false. However, this can be changed. This environment variable can be changed in case you would want to access the CPU as a SYCL device. And so if you're just interested in the CPU, you can change this environment variable to be equal to OpenCL CPU. However, if you're interested in both CPU and GPU visibility, then you can specify both as done here in this README. That way you can see both all the 12 GPU devices as well as the 2 CPU sockets. The other thing to note, as I mentioned, that by default, DPNP and DP control see 12 GPU devices. So that's 6 PVCs times 2 tiles each. And that's because of this Z flat device hierarchy. So here there's a bit of a difference between the default with and without the AI frameworks module. The default without the frameworks module is to set this environment variable to composite, which means that the visibility is of the 6 PVC tiles with then a layer of each PVC GPU, and then an extra layer of each PVC GPU having 2 tiles each. But the frameworks module sets that to flat. What this means is that it exposes the 12 tiles directly. So that's why in the previous examples, we saw that DP control, for example, saw 12 GPU devices right out of the box. You can toggle between these two, but we really recommend for any sort of Python or AI framework activity to set this environment variable to the default, which is default for the frameworks module, which is to set it to flat. The other thing to mention is that DPNP and DP control kernels, when you run them on the GPUs, they run asynchronously in linear order. So this is pretty similar to PyPy or even, for example, PyTorch. What this means is that the kernel is launched from the host of the device, but then execution of the program doesn't actually wait for the kernel to finish, right? Instead, it allows to proceed and queue more kernels to the GPU. So this is actually a desirable model since it results in faster runtime and you can utilize the GPUs better as well. But again, similar to how you would do, you would use PyTorch if you're experienced with that. If you're interested in timing some kernels, you need to make sure that you do this appropriately. If you don't actually wait for the SYCL queue of a particular call to return, then really all you're measuring is the kernel launch time rather than the execution of the kernel on the device. And so there's a little example demonstrating that. So here we're doing a simple matrix multiply with DPNP. So we set the array size and then we initialize an array, which is just a square of the size. We do a bit of warm up, but then you can see here we're timing the kernel in the default async mode. So here we're just basically putting timers with tick and tock around this y equals mp map call. And then printing the time, and I'll go to the expected output later. And then the appropriate way of doing this is that you then put a SYCL queue wait call on the output array. So what this does is it forces the SYCL queue to return so that the execution of the program doesn't continue until that kernel is actually done executing on the GPU. And so, for example, if we look at the bottom at the expected output with the asynchronous execution, you see that the runtime is less than 1 millisecond. So that's really just the kernel execution time. But instead, the actual kernel time is on the order of 0.3 seconds here, 0.35. So this is the real runtime of the kernel. So just something to keep in mind as they're using these tools, as well as even PyTorch in terms of timing execution on the device. The last package to cover is Numba DPEX, which is Intel's extension for Numba. And this allows you to apply non-budget compiler to generate performant parallel code on Intel GPUs. So this is using LLVM-based code generator, and they implement a new kernel programming API. They call this KAPI. In pure Python that's modeled after the SYCL API, and you'll see that in a second. So there's an example here that does a simple, actually, oh, apologize for that. Let's open it this way then. Okay. I'll fix that link later. So this NumPy example, you can see that it's doing a simple vector addition. It's just taking two vectors, adding in an element-wise fashion, and then storing the results in an output array. But let's go through some of these key parts of this simple program. So first, you can see that we're actually importing DPNP2, and I'll come to that in a second. But then we import NumPy DPEX and this kernel API that I mentioned. So anytime you have a function, a Python function that you're trying to execute on the GPU, you would need to decorate that function with this dpex kernel decoration here. And this means that this function will be executed or implemented on the device as a basic parallel for calculation. So in this case, what that means is that each work item performs the same calculation on the subset of the data, which is the SPMD model that you may have seen yesterday in some of the programming models as well. So looking at this function, you can see that it actually takes this work item as the initial argument, and then the arrays are passed in the subsequent arguments to the function. And the first thing you do is actually to get that work item. So what this is doing is then, this particular work item is selecting a particular element of these arrays. And so in this way, we're really doing an element-wise sum of these two vectors. Once again, NumPy DPEX follows the compute follow data programming model. What this means is, again, that all we have to do is instantiate or initialize the input and output arrays on the device. And then the NumPy DPEX kernel will actually run on that same device. So here we're using DPNP, and you can see I'm using the default option, which is GPU 0. So this kernel is running on GPU 0. Then the other thing you need to do before launching the kernel is you need to define the amount of work, basically the number of work items, and this is done with this dpex range API. And in this case, we're doing one work item per array value. So we're passing n here, which is the length of the vectors, as the number of work items. What this means is effectively each work item will do the summation of an individual element of these vectors. Finally, at the bottom, you can see that we call this kernel. And again, as I mentioned, each work item in the range executes this spec add function, as you saw here. At the bottom here, you'll see how we actually do that. You need to pass the function that you're trying to run on the GPU, the number of work items, and then the input and output arrays. And you see at the bottom, we just do a simple check to make sure that the sum is actually computed successfully. So pretty easy example, but I think it highlights the main ideas behind NumPy DPEX. And if you're familiar with NumPy and NumPy then that should be pretty straightforward as well. You can do more complicated data parallel kernels in NumPy DPEX. These are called ND range kernels. So this is how, for example, you would implement a matrix multiply, but we left those sort of as further reading, and you can find a link there to the documentation that goes through that. The final topic I wanted to cover today is DLPack. So this is a way that you can actually integrate the Intel Python stack that I just covered today with the AI software stack, in particular PyTorch. So effectively, DP Control is supports the Python Array API standard. As I mentioned earlier, DP Control is really sort of a layer underneath DPNP. So what that means is that it gives you interoperability with really any other Python library that follows the same standard. And NumPy and PyTorch are examples of those libraries, which means that through DLPack, we can do zero copy data access across the Python ecosystem. So for example, let's open this this simple DLPAC code that I have included here, you can see that we import DPNP and PyTorch both. And then I'm here demonstrating interoperability both ways. So we first create a torch array and we allocate that on the XPU device. You'll see later this is how you access the Intel GPUs. You can then create a DPNP array by calling this DP from DLPAC and passing the PyTorch array. What this does is actually DP array is really just a view of the memory of that torch array. So now, for example, we can modify the PyTorch array. In this case, we just modify the first element of it. And then we can print both the original PyTorch array and the DPNP view of the PyTorch array. And so if we go to the expected output at the bottom, you'll see the original PyTorch array, which was initialized with a range, so it's supposed to be 0, 1, 2, 3, but we then modified the first entry to be -2. You then see that the DPNP view of that array is actually the same. But we did that by just modifying the PyTorch array. So it really is just a view of the memory that was initialized or really controlled still by PyTorch. And again, you can see that the devices match. And then the second piece of this code is just showing that interoperability goes the other way. That is, you can initialize a DPNP array, but you can create a zero copy view from PyTorch as well. So what this means is that if you have a complicated pipeline that is doing a mix of say NumPy and PyTorch, when you come to Aurora and run that on Intel GPUs, you can then replace the NumPy part with DPNP and offload that part to the GPUs as well. And then if you need to go from DPNP to PyTorch, you can do that without actually having to duplicate any of the arrays. And so that allows for performant code, both in terms of computational efficiency and also memory efficiency. Yeah, so that's really the last piece here. There's some notes about using DLPAC on Aurora. I won't cover those just in the interest of time, but you can go over them just to make sure that you are sort of aware of just a few gotchas maybe. The biggest one is really just this device flight hierarchy must be set to flat. Yeah, so I'll stop here and then make way for the next part of the talk, which will move from not just how to do Python on Intel GPUs, but actually how to do AI and machine learning on Intel GPUs.
Thank you, Riccardo. Nice talk.